Google Cloud Platform, Unlocking the Future of Cloud Computing. Chapter 1, Introduction to Google Cloud Platform. Welcome to Google Cloud Platform or GCP, where we take a journey into the world of cloud computing. In today's digital landscape, the cloud is not just a technology. It's the foundation of innovation, growth, and limitless possibilities for businesses of all sizes. GCP is one of the leading cloud platforms globally, offering a wide range of services that empower developers, engineers, data scientists, and enterprises to build, scale, and operate their applications efficiently. In this audiobook, we'll explore the most important services provided by GCP, their real-world applications, and how they are transforming industries. Whether you're new to the cloud or an experienced professional, this guide will offer valuable insights into Google's powerful suite of tools and services. Let's begin our journey by understanding the core concepts of cloud computing and how GCP fits into this ecosystem. Chapter 2, Compute Services, Powering Your Applications. Imagine being able to run any application, at any scale, with the infrastructure entirely managed for you. That's the power of GCP's compute services. At the heart of these services are Google Compute Engine and Google Kubernetes Engine, the backbone of many of the world's largest applications. Google Compute Engine. Compute Engine is GCP's infrastructure as a service, offering scalable virtual machines. Whether you need to run a single instance or scale to thousands of VMs, Compute Engine gives you the flexibility to choose machine types, storage, and networking. You can run your workloads in virtualized environments without worrying about hardware constraints. With Compute Engine, you also benefit from features like live migration, which allows your VMs to continue running without interruption, even during system updates. And with custom VMs, you're no longer bound by predefined machine types. You can choose the exact amount of CPU, memory, and storage you need. Imagine you're building an application that requires high-performance computing for rendering 3D graphics. Compute Engine allows you to spin up high-powered virtual machines with GPUs to accelerate these tasks. And when the job is done, the instances can be stopped, and you only pay for what you used. That's cloud efficiency. Key concepts of Compute Engine. Virtual machines. VMs. Virtual machines are the backbone of Compute Engine. They are instances that simulate a physical computer, enabling you to run applications and services without having to manage the physical hardware. When you create a VM on Compute Engine, you specify the operating system, the machine type, and the amount of storage and memory you need. Machine types? Google Cloud provides several machine types, from predefined configurations to custom machines that allow you to choose exactly how many virtual CPUs, vCPUs, and how much memory your instance should have. Predefined machine types are generally categorized into standard, high memory, high CPU, and shared core types, each suited for different kinds of workloads. Storage options. Compute Engine also offers multiple storage options to suit your workload requirements. These include standard persistent disks, solid-state drives, SSD, and local SSDs for high-performance use cases. Persistent disks can be attached to instances and are automatically replicated for redundancy, while local SSDs provide high-speed temporary storage. Networking. Networking is critical in any cloud environment, and Compute Engine offers a highly customizable virtual private cloud, VPC, that allows you to define your own networking parameters. You can set up firewalls, VPNs, load balancers, and even manage network traffic through Google's global network infrastructure. Creating and managing VM instances. Creating your first VM. When you first create a VM instance, you'll have several options to configure it to your specific needs. You can choose the operating system, either from a list of pre-built images such as Linux, Windows, or create your own custom image. You can also choose the machine type, the disk type, and additional options like firewall rules and startup scripts. Auto-scaling and instance groups. One of Compute Engine's most powerful features is its ability to scale. You can group multiple instances into what's called a managed instance group, which can automatically scale up or down depending on the workload. For example, if your web application is seeing an increase in traffic, new instances can be added to the group automatically. Once the traffic subsides, these instances can be terminated, saving you costs. Snapshots and backups. Managing backups is crucial to ensure data integrity and disaster recovery. Compute Engine allows you to create snapshots of your persistent disks, which can be used to back up data or restore an instance to a previous state. Advanced features and best practices. Preemptible VMs. Google Cloud offers a special type of virtual machine known as preemptible VMs. These are short-lived, cost-effective VMs that can be preempted by Google Cloud at any time if the resources are needed elsewhere. However, for batch processing or other time-flexible workloads, preemptible VMs can be a great way to save costs. Custom machine types. If none of the predefined machine types fit your workload, Google Cloud allows you to create custom machine types with specific vCPU and memory combinations. This is particularly useful when you have workloads with unique resource requirements. Security best practices. When running workloads on the cloud, security is paramount. Google Compute Engine offers several layers of security, from IAM, identity and access management, roles that restrict access to resources, to firewall rules that limit the traffic to and from your instances. It's essential to adopt best practices such as setting up two-factor authentication, (2FA), using SSH keys instead of passwords for accessing VMs, and regularly updating your VM instances with security patches. Monitoring and logging with Compute Engine. Stackdriver for monitoring. Monitoring the health of your instances is key to ensuring uptime and performance. Google Cloud offers Stackdriver, now part of Google Cloud Operations, to help you monitor your Compute Engine instances. You can track metrics such as CPU usage, memory, and disk input-output, and set up alerts that notify you if any threshold is exceeded. Cloud logging? With cloud logging, you can collect, filter, and analyze logs from your Compute Engine instances. These logs provide valuable insights into the health of your systems, helping you diagnose issues, optimize performance, and maintain security. Cost optimization on Compute Engine. Right-sizing recommendations. Google Cloud provides right-sizing recommendations for your instances based on actual usage. If your instance is underutilized, you can resize it to a smaller machine type, helping you save on costs. Committed use contracts and sustained use discounts. For workloads with predictable usage, Google Cloud offers committed use contracts that allow you to lock in lower pricing for VMs in exchange for a 1 or 3 year commitment. Sustained use discounts automatically apply when you run VMs for a large portion of the month, helping you reduce costs without any additional configuration. Real-world use cases and industry applications. Web applications and APIs. Compute Engine is widely used for hosting scalable web applications and APIs. Using auto-scaling and load balancing, you can ensure that your applications remain available even during traffic spikes. High-performance computing, HPC for industries like genomics, financial modeling, and scientific simulations. Compute Engine's high-performance machines and GPUs offer the necessary compute power for demanding tasks. You can spin up thousands of instances to parallelize your workloads, drastically reducing the time it takes to get results. Game servers and rendering farms. Many gaming companies use Compute Engine to host multiplayer game servers and to run rendering farms. With GPUs and high-performance instances, Compute Engine enables real-time gaming experiences and fast 3D rendering. The future of Compute Engine. Innovations and trends. As cloud computing continues to evolve, so does Compute Engine. Innovations such as serverless VMs, edge computing, and tighter integration with AI/ML services are shaping the future of how we run and manage workloads in the cloud. Compute Engine remains at the forefront of these advancements, continually pushing the boundaries of what's possible with virtualized infrastructure. Google Kubernetes Engine. For developers embracing containers, Google Kubernetes Engine, or GKE, is a game-changer. Kubernetes has become the industry standard for container orchestration, and GKE offers a fully managed version of this powerful platform. With GKE, you can deploy and manage containerized applications without the complexity of manual scaling, load balancing, or cluster management. Let's take an example. Imagine a company that runs a suite of microservices for their e-commerce platform. Each microservice runs in a container, handling different tasks like user authentication, payments, and product recommendations. With GKE, this company can manage these microservices efficiently, ensuring that each service scales independently based on demand. If traffic surges during a holiday sale, GKE automatically scales the containers, keeping the application responsive. Google Kubernetes Engine, GKE, is a managed production-ready environment for running Kubernetes applications. In this chapter, we dive into the basics of GKE, what it offers over self-managed Kubernetes clusters, and how it integrates with other Google Cloud services. We will walk you through setting up your first GKE cluster, explore the GKE architecture, and discuss the benefits of using GKE for running containerized applications in the cloud. In essence, GKE abstracts away the heavy lifting of managing the underlying infrastructure, so developers and DevOps teams can focus on deploying and running their applications rather than dealing with the complexities of cluster management. Let's break it down into 2 key components. Kubernetes, a powerful platform that automates the deployment, scaling, and operation of containerized applications. Google Kubernetes Engine. GKE, Google Cloud's fully managed Kubernetes service that integrates with Google Cloud Platform, GCP, to provide you with a streamlined, production-ready Kubernetes environment. Why Kubernetes? Before diving into GKE, it's helpful to understand why Kubernetes is so popular in the first place. Kubernetes allows developers to manage containerized applications with ease, providing features such as container orchestration, automating the deployment, scaling, and management of containerized applications, self-healing, automatically restarting failed containers, rescheduling containers when nodes die, and rolling back changes without manual intervention, declarative configuration, using configuration files, YAML JSON, to define the desired state of your application. Scalability, scaling applications seamlessly in response to traffic and demand. Kubernetes provides these features in any environment, on-premises or cloud, but managing Kubernetes yourself requires a deep understanding of infrastructure, networking, security, and maintenance. This is where GKE steps in. What does GKE offer over self-managed Kubernetes clusters? Managing your own Kubernetes cluster can be complex and resource-intensive. GKE simplifies the entire process by offering a managed Kubernetes experience. Here's what GKE offers over self-managed Kubernetes clusters. Automated infrastructure management. With self-managed Kubernetes clusters, you are responsible for managing the infrastructure, including provisioning servers, nodes, setting up the Kubernetes control plane, configuring networking, and handling updates. GKE automates all of these tasks. Automatic cluster provisioning. GKE provisions and configures the Kubernetes control plane, master, and worker nodes for you. This saves time and ensures you're working with best practices from the start. Node management. GKE automatically handles the lifecycle of your nodes, including node upgrades, patching, and scaling based on your workloads. Control plane management. Google manages the Kubernetes master components, ensuring high availability and fault tolerance, with no need for manual intervention. Automatic upgrades and patching. One of the key challenges in managing a Kubernetes cluster is keeping the system up to date with the latest patches and versions. Security patches, in particular, are crucial for protecting your infrastructure. With GKE, Automatic Kubernetes version upgrades, GKE can automatically upgrade both your master node and worker nodes to the latest Kubernetes version, ensuring that your cluster is always secure and running efficiently. Security patching. GKE automatically applies security patches to the underlying infrastructure and Kubernetes components without downtime. In a self-managed environment, you would need to manually monitor and apply updates to Kubernetes, which can be error-prone and time-consuming. Built-in autoscaling. Kubernetes supports autoscaling, but setting it up in a self-managed environment can be complex. GKE simplifies autoscaling with built-in features. Cluster Autoscaler automatically adjusts the number of nodes in your cluster based on resource demands. Horizontal Pod Autoscaler scales your application by adjusting the number of pod replicas depending on CPU, memory usage, or other custom metrics. This allows your infrastructure to scale up during peak demand and scale down during low traffic periods, optimizing both performance and cost. Security and compliance. In a self-managed cluster, you are responsible for configuring and maintaining security policies. GKE enhances security with built-in features. Google Managed Security. GKE's control plane is protected by Google's infrastructure security practices. Your nodes are also protected by Google's security architecture. Role-based access control. RBAC GKE offers easy-to-use RBAC to control who can access the cluster and what permissions they have. It also integrates seamlessly with Google Cloud Identity and Access Management, IAM, for additional control. Network security. GKE provides built-in support for private clusters, VPC native networking, and Kubernetes network policies to control traffic between pods. By leveraging Google Cloud security features, GKE provides a robust environment that simplifies compliance with industry standards like HIPAA, PCI DSS, and others. Monitoring and logging. In a self-managed Kubernetes environment, setting up monitoring and logging requires additional tools and configuration. GKE integrates seamlessly with Google Cloud's powerful monitoring and logging services. Google Cloud Operations Suite, formerly Stackdriver, automatically collects logs and metrics from your cluster and integrates them into a unified dashboard for monitoring, logging, and alerting. Pre-configured dashboards. GKE comes with pre-configured dashboards that show the health and performance of your cluster, including CPU usage, memory, network traffic, and errors. This eliminates the need to manually configure monitoring tools and ensures you have complete visibility into your cluster's performance. GKE's seamless integration with other Google Cloud services. One of GKE's biggest advantages is its deep integration with other Google Cloud services. This allows you to extend your applications and clusters with the full power of the Google Cloud ecosystem. Here are some of the key integrations. Google Cloud Storage and Persistent Disks. GKE integrates with Google Cloud's persistent storage options, making it easy to handle both ephemeral and stateful workloads. Persistent Volumes. PVs automatically provision persistent disks, PDs, for your applications that require durable storage. Google Cloud Storage, GCS. Easily connect your GKE applications to Google Cloud Storage buckets for object storage needs. Cloud Build and Continuous Integration and Continuous Deployment, CI/CD. GKE integrates with Cloud Build, Google's CI/CD service, allowing you to automate building, testing, and deploying your containerized applications to GKE. Cloud Run for serverless deployments. For applications that don't need full Kubernetes cluster management, GKE integrates with Cloud Run to enable serverless workloads that run directly on GKE clusters, BigQuery and data analytics services. For data-heavy applications, GKE integrates with Google's data analytics tools such as BigQuery and Dataflow. You can easily move data between your GKE applications and Google's data processing services. AI and machine learning. If you're building AI or machine learning applications, GKE integrates with Vertex AI and other Google Cloud AI tools. You can train, deploy, and serve machine learning models on GKE using Google's AI infrastructure. Cost management with GKE. Managing costs in Kubernetes can be difficult, but GKE provides tools to help you optimize spending. Preemptible VM nodes. GKE supports preemptible VMs, which are low-cost, short-term instances that can significantly reduce infrastructure costs. Autopilot mode. For even greater simplicity and cost savings, GKE offers Autopilot mode, which eliminates node management altogether and charges only for the resources your workloads use. Setting up your GKE environment. Setting up your Google Kubernetes Engine (GKE) environment for the first time can feel like embarking on a new adventure in cloud computing. You're about to dive into a platform that gives you the power of Kubernetes, one of the most popular container orchestration systems, without all the complex management that usually comes with it. Picture this: instead of worrying about provisioning servers or handling security patches, you're free to focus on building and deploying your applications. So, let's walk through the process of setting up your GKE environment in a more narrative way, one step at a time. Opening the door to Google Cloud? It all begins with Google Cloud Platform, GCP, the home of GKE. If you don't already have an account, your journey starts by signing up at cloud.google.com. GCP welcomes you with a set of free credits, enough to get you started and play around without worrying about costs right away. After signing up, you'll create your first project, a sort of container within GCP where everything you build and deploy will live. Think of this project like your personal workshop, where all your Kubernetes clusters, apps, and resources will be organized. Once you've named your project, GCP asks you to enable billing even if you're using free credits. Don't worry, you can set up alerts and budget controls to keep track of spending, but for now, this is just to make sure the wheels are greased for when your GKE clusters start running. Enabling the Kubernetes Engine API. Now that your GCP account is ready, it's time to unlock the magic of GKE. In GCP, there are countless services, from machine learning to data analytics, but for now, you need to focus on Kubernetes. You'll do this by enabling the Kubernetes Engine API, the tool that makes it possible to create and manage Kubernetes clusters on Google Cloud. Think of it like flipping a switch that turns on the engine for all your future Kubernetes operations. From the GCP dashboard, you head over to APIs and services, and with a few clicks, you search for Kubernetes Engine API and enable it. It's like opening the gates to a vast Kubernetes-powered kingdom, where GKE will now manage your infrastructure and workloads behind the scenes. Installing the tools? You've unlocked the power of GKE, but now you need the right tools to command it. On your local machine, you'll want to install the Google Cloud SDK, which gives you the GKE Cloud Command Line tool, your primary tool for interacting with Google Cloud services. With a quick download and a few commands, the SDK is installed, and you run GKE Cloud in it to authenticate yourself and set up your project. Next comes Kubectl, the essential tool for communicating directly with your Kubernetes clusters. If GKE Cloud is your gateway to Google Cloud, then Kubectl is your wand, casting commands to manage pods, services, and deployments. You install it in just one, GKE Cloud Components install Kubectl. Now you're ready to take control of your Kubernetes clusters, from spinning up applications to scaling them seamlessly. Creating your first cluster. The moment has arrived. You're about to create your very first Kubernetes cluster on GKE. This is the heart of your environment, the infrastructure where your applications will live, scale, and run. You head back into the GCP console and navigate to Kubernetes Engine greater than clusters. Clicking Create Cluster feels a bit like launching a rocket, even though the process is fairly simple. You're given two main options for your cluster. Standard cluster. If you want full control over how the cluster is managed, this is your go-to. You'll be able to configure everything from node types to scaling settings. Autopilot cluster. For those who prefer to offload most of the management to Google, this mode is perfect. Autopilot manages the infrastructure for you, optimizing nodes and scaling automatically. After choosing the mode that best fits your needs, you name your cluster. Maybe something like Prod Cluster 1 if you're setting up for production, or Test Cluster if you're just experimenting. You also decide where the cluster will live, picking a region or zone depending on your performance and availability needs. With a few more clicks, GKE starts provisioning your cluster, setting up the Kubernetes control plane and nodes behind the scenes. This part feels almost magical. The infrastructure is being built without you having to touch a single server or worry about how it's configured. Connecting to your cluster. Once GKE has finished building your cluster, it's time to connect and start working with it. This is where your Kubectl tool comes into play. By running a simple command, you authenticate your local machine to manage the cluster. GKE Cloud Container Clusters get credentials cluster_name_zone. This command pulls down the necessary credentials and configures Kubectl so you can interact with your cluster, issuing commands to create applications, scale workloads, and manage resources. Suddenly, you're connected. Your terminal is ready, and a few test commands confirm that everything is set up. Maybe you run Kubectl get nodes to see the cluster's nodes humming away in the background, waiting for your next instruction. Fine-tuning with IAM and permissions. Now that your cluster is up and running, the next thing you consider is security. Who can access your cluster? Who can deploy applications? GKE integrates tightly with Google Cloud's Identity and Access Management (IAM), allowing you to define roles and permissions with precision. In the GCP console, you can assign roles like Kubernetes Engine Admin for full control, or Kubernetes Engine Developer for application management. This is like setting the rules in your workshop. Only those with the right tools and permissions can work on specific parts of your Kubernetes environment. Using the GKE Cloud command or the GCP console, you define these roles and start locking down who can do what in your cluster. Networking and security. At this point, you may start thinking about how traffic flows into your cluster, or how secure the communication between pods and services is. GKE provides a range of networking options, including VPC native clusters, which allow you to manage your Kubernetes networking within Google Cloud's Virtual Private Cloud (VPC). This means you can integrate your GKE cluster into a private network, controlling traffic and enhancing security. You can also opt for private clusters, which restrict access to your Kubernetes control plane, further locking down who can access and manage your infrastructure. Auto-scaling and monitoring. Keeping things running smoothly. Your cluster is now running, but how do you ensure it adapts to changing demands? GKE has you covered with auto-scaling features, allowing your cluster to grow or shrink based on real-time traffic and resource needs. Setting up Cluster Autoscaler is simple and ensures your nodes scale up when demand increases and down when it's quiet. No need to monitor and manually adjust. GKE takes care of it. And speaking of monitoring, GKE integrates with Google Cloud Operations Suite, providing you with real-time insights into your cluster's performance. Logs, metrics, and alerts are all available in pre-configured dashboards, helping you keep track of resource usage, potential bottlenecks, and overall cluster health. Deploying applications on GKE. Now that you have your GKE environment ready, it's time to deploy applications. Kubernetes is all about containers, so if your app isn't already in a container, that's your first task. Containers ensure your app runs consistently no matter where it's deployed. You'll typically use Docker to containerize your application. Here's a quick reminder of how you'd create a Docker image for your application. Assuming you have a Docker file in your project directory, you can build an image like this. Docker build tgcr.io project_id/myappv1. This command creates a Docker image for your app and tags it with the name myapp and version v1. Note the prefix gcr.io project_id, which refers to Google Container Registry, GCR, the place where you'll store your images. GCR is a fully integrated Docker registry provided by Google Cloud. Push your Docker image to Google Container Registry, GCR, before deploying your app on GKE. Your container image needs to be accessible by the Kubernetes cluster. GKE clusters can pull images directly from Google Container Registry, GCR, so the next step is to push the image you built in the previous step to GCR. Docker push gcr.io project_id/myappv1. This command uploads your container image to GCR, where it can be used by GKE. Think of GCR as the storage hub for your Docker images, ensuring they're available and secure for deployment. Create a Kubernetes deployment. Now that your container image is safely stored in GCR, it's time to define how Kubernetes will run your application. This is done using a Kubernetes deployment, which specifies the desired state of your application, such as how many replicas or instances you want running, the Docker image to use, and how to handle updates. You can define a Kubernetes deployment using YAML file. YAML file describes your application deployment. Replicas, you're telling Kubernetes to run number instances of your application for redundancy and load balancing. Image, this is the Docker image you pushed to GCR earlier. Port, Kubernetes will expose port on your container, assuming your application is running a web server on that port. To deploy the app, you simply apply the YAML file using Kubectl. Kubectl apply fdeployment.yaml. With this single command, Kubernetes creates the necessary pods, individual instances of your app, pulls the image from GCR, and schedules them to run on available nodes in your GKE cluster. You can now sit back and let Kubernetes manage the deployment. Expose your application to the internet. After deploying your app, you'll want users to be able to access it. Kubernetes uses a service to expose your application to the outside world, either internally within the cluster or externally to the internet. You should write YAML file for a load balancer service, which will expose your app with an external IP address. This service will create an external load balancer. Thanks to GCP's integration with Kubernetes, and assign a public IP address to your app, allowing users to access it via the internet. You can apply the service configuration like this. kubectl apply fservice.yaml. Once applied, Kubernetes provisions a load balancer on Google Cloud and assigns an external IP to route traffic to your pods. To find out the IP address, run the following command. kubectl get services. After a few moments, the external IP will appear, and users can access your app by navigating to that IP in their browser. Scaling your application. One of the core benefits of GKE and Kubernetes is effortless scaling. Let's say your app is experiencing increased traffic, and you need more instances to handle the load. You can easily scale your deployment manually or set up auto-scaling. Manual scaling? You can manually scale the number of replicas with a simple command. kubectl scale deployment, my app deployment replicas equals 5. This command increases the number of app instances, pods, from 3 to 5. Kubernetes will automatically schedule and run the additional pods on available nodes in your cluster. Autoscaling? If you want GKE to handle scaling for you based on resource usage, you can enable the horizontal pod autoscaler. This scales the number of pods based on CPU or memory usage thresholds. For example, to set up autoscaling based on CPU utilization, use a command. kubectl autoscale deployment my app deployment, CPU % equals 50 min equals 3 max equals 10. This command configures Kubernetes to automatically scale your deployment between 3 and 10 pods, depending on CPU usage. If CPU utilization exceeds 50%, Kubernetes will add more pods to distribute the load. Rolling updates for zero downtime. In the real world, applications often need updates, whether it's to deploy new features, fix bugs, or update the underlying image. GKE allows you to perform rolling updates, ensuring zero downtime for your users. To update your deployment to a new version of your app, for example, V2, you simply update the image in the deployment configuration. kubectl set image deployment /my app, deployment my app equals gcr.io, project_id /my app v2. Kubernetes will gradually terminate old pods, running V1, and replace them with new pods running V2, all while ensuring that your app stays available. It does this by updating a few pods at a time, monitoring their health, and only proceeding if the new pods are running smoothly. If something goes wrong during the update, for instance, if the new version of the app crashes, Kubernetes can automatically roll back to the previous version, minimizing any impact on your users. Monitoring and logging. Once your app is deployed and running, monitoring its health and performance becomes essential. Fortunately, GKE integrates with Google Cloud's Operations Suite, formerly Stackdriver, to provide built-in monitoring and logging. You can easily set up logging and metrics collection in GKE to keep an eye on how your app is performing, tracking things like CPU and memory usage, response times, and any error logs. To view logs for your app, you can use the kubectl command. kubectl logs, pod_name. This shows the logs of a specific pod, helping you debug issues or understand how your app is behaving in real time. For a more comprehensive view, you can head into the Google Cloud Console, where GKE offers dashboards with pre-configured metrics and logging. You'll have complete visibility into your app's health, and you can set up alerts to notify you if anything goes wrong, such as high CPU usage or failed pods. Networking in GKE. Networking in GKE is robust and deeply integrated with Google Cloud's network infrastructure. Whether you're running a simple web application or a complex microservices architecture, GKE provides the tools you need to manage networking, expose your services, and secure your applications. From pod-level communication to load balancing and network policies, understanding these core concepts will help you build scalable, secure, and high-performing cloud-native applications on GKE. Understanding pod networking. In Kubernetes, the basic unit of deployment is the pod, which can host one or more containers. Each pod is given its own IP address, allowing it to communicate directly with other pods in the cluster. This is called the pod IP network. Pod-to-pod communication. By default, all pods in a Kubernetes cluster can communicate with each other, regardless of which node they are running on. This is possible because Kubernetes implements a flat network model, meaning every pod is assigned a unique IP address that is routable within the cluster. Pod IP address management. In GKE, pods receive their IP addresses from the underlying Google Cloud, Virtual Private Cloud, VPC, network. Kubernetes uses an overlay network, such as Calico or VPC native routing, to ensure pods can communicate, even across different nodes. Each time a new pod is created, GKE dynamically assigns it an IP from the cluster's network range, ensuring pods can discover and communicate with one another easily. Kubernetes services, connecting pods. Pods are ephemeral by nature. They can be created and destroyed based on demand. To provide stable, consistent access to your applications running in pods, Kubernetes uses services. A service is an abstraction that exposes your pods to other applications or users, either within the cluster or externally. Types of services in GKE. Cluster IP, internal traffic. This is the default service type in Kubernetes. A cluster IP service exposes your pods to other services and pods within the cluster but not to external traffic. Kubernetes assigns the service a stable, internal IP address, which acts as an entry point to access the pods behind the service. Example use case: imagine you have a front-end service that needs to communicate with a back-end database service. Both services run inside the GKE cluster, so you'd use a cluster IP to route traffic internally. Node port, external traffic. A node port service allows external users to access your application through a static port on each node of the cluster. When a request hits the node port, Kubernetes forwards the traffic to the appropriate pod running your application. While node port is useful for exposing services to the internet, it's often used as a building block for higher-level services like load balancer. Load balancer, public IP. The load balancer service is the most common way to expose your application to external users. It automatically provisions a Google Cloud load balancer, assigns a public IP address, and distributes traffic to your pods. This makes it ideal for web applications that need to be accessible over the internet. Example: when deploying a web app, you might use a load balancer service to allow users to connect to the app through a public IP. You should write a YAML file to define a load balancer service in Kubernetes. When this service is created, Google Cloud will provision an external load balancer, and the service will get a public IP address through which your app can be accessed. Ingress, advanced traffic management. While a load balancer service works well for simple use cases, you might want more advanced traffic management features, like URL-based routing, SSL termination, and custom domain names. This is where Ingress comes into play. Ingress is a Kubernetes resource that provides a more powerful way to route traffic to your services. Rather than exposing each service with its own load balancer, Ingress allows you to consolidate multiple services under one external load balancer and configure rules for how traffic should be routed. Key features of Ingress. Path-based routing. Ingress lets you define rules so that traffic to specific paths, for example, API or /login, is routed to different services in your cluster. Host-based routing. You can route traffic to different services based on the host header. For example, api.masite.com versus www.masite.com. SSL termination. Ingress allows you to manage SSL certificates and terminate HTTPS traffic at the load balancer, so your application doesn't have to handle encryption directly. Ingress resource is created using YAML file. This Ingress resource directs all traffic to myapp.example.com to the MyApp service running in your GKE cluster. Once the Ingress resource is applied, GKE automatically provisions a Google Cloud HTTP's load balancer, enabling you to route traffic to different backend services based on the rules you define. VPC native clusters. In GKE, you can choose between VPC native or routes-based clusters, with VPC native being the recommended option for most scenarios. VPC native clusters integrate more closely with Google Cloud's virtual private cloud, VPC, allowing you to manage Kubernetes networking with better scalability, security, and flexibility. Benefits of VPC native clusters. Pod IPs as first-class citizens. In VPC native mode, each pod gets its own unique IP address within the VPC network, making pod IPs routable within your Google Cloud VPC. This makes it easier to connect your GKE clusters with other Google Cloud services, like databases or APIs, and even on-premises resources. Subnets and private networking. You can configure VPC native clusters to use specific subnets, giving you better control over the network range for your pods. You can also enable private clusters, where nodes and pods only have internal IP addresses, improving security by restricting access to your cluster from the public internet. Network policies. With VPC native clusters, you can define network policies to control the flow of traffic between pods and services. This allows for more granular security, where you can specify which pods are allowed to communicate with each other, enhancing security within the cluster. To create a VPC native GKE cluster, you'll specify the Enable IP alias flag when creating the cluster via gcloud. GKE Cloud Container Clusters create my cluster enable IP alias. This ensures that your pods are assigned IP addresses from the VPC subnet and enables the features of VPC native clusters. Private clusters and internal load balancing. For sensitive workloads, you might want to isolate your GKE cluster from the public internet entirely. Private clusters allow you to run Kubernetes nodes and control plane components with only internal IP addresses, ensuring that the cluster can only be accessed via the internal VPC network. In a private cluster, nodes in the Kubernetes control plane are not exposed to the public internet. You can still expose services to external users via Google Cloud load balancers, but the nodes themselves remain private. You can use internal load balancers, ILB, to expose services within the VPC without assigning a public IP. YAML file should be written to define the service which creates an internal load balancer that allows traffic from within the VPC to reach your service without exposing it to the internet. Network policies, securing pod communication. In large clusters or multi-tenant environments, you might need to limit which pods can communicate with each other. Kubernetes network policies allow you to define rules controlling pod-to-pod communication based on labels. For example, you could define a policy that allows only your front-end pods to communicate with your back-end pods using YAML file. This policy allows traffic from any pod with the front-end label to the pods labeled back-end, effectively isolating the back-end from any other pod. CloudNAT and egress traffic. When running a private cluster, you might still need your pods to access external resources, like APIs or updates. In such cases, GKE uses CloudNAT, network address translation, to allow pods with internal IP addresses to initiate outbound connections to the internet. CloudNAT ensures your private cluster remains secure while still enabling outgoing internet traffic from your pods. Storage solutions in GKE. One of the key aspects of deploying modern applications is persistent storage. In this chapter, we'll explore how GKE manages storage through persistent volumes, PVs and persistent volume claims, PVCs, integrating seamlessly with Google Cloud Storage. We will also discuss how to manage stateful applications in Kubernetes, such as databases and other storage-bound services. Managing GKE clusters with Kubernetes operators. Kubernetes operators extend Kubernetes capabilities, allowing developers to manage complex applications more effectively. At its core, a Kubernetes operator is a custom controller that uses the Kubernetes controller pattern to manage the deployment, scaling, backup, updates, and failure recovery of complex applications in a Kubernetes environment. The operator is a method of packaging, deploying, and managing a Kubernetes application using custom resource definitions, CRDs, which extend Kubernetes with additional APIs specific to the application being managed. Why use operators? The main reason for using an operator is to automate the management of applications and services that typically require manual intervention. Stateful applications like databases, for example, PostgreSQL, MySQL, message queues, for example, RabbitMQ, or distributed systems, for example, Cassandra, Kafka, have complex operational requirements, such as data replication, backups, and failure recovery. Operators encapsulate this domain-specific knowledge in a programmatic way, making it easier to deploy and operate these applications on Kubernetes. In essence, operators encode operational knowledge into software, transforming what would normally require a skilled human operator into an automated Kubernetes native process. Custom resource definitions. CRDs operators use custom resource definitions, CRDs, to extend Kubernetes with new types of resources. These resources are often representations of specific applications or services, for example, databases, storage systems. A CRD allows you to create and manage new types of resources in your Kubernetes cluster beyond the default ones, such as pods, deployments, services, etc. For example, if you are building an operator to manage a PostgreSQL database, you would define a custom resource type called Postgres cluster. This resource could include specifications for the number of database replicas, backup schedules, and other operational configurations. A sample CRD for a PostgreSQL cluster might look like YAML. File with commands. AP version middatabase.io/v1alpha1, kind Postgres cluster, metadata, spec. This allows Kubernetes users to interact with Postgres cluster just like they would with native resources like deployments or services, using kubectl commands to create, update, or delete them. Lifecycle management with operators. Operators manage the full lifecycle of an application, from deployment to updates, scaling, backups, and recovery from failures. Here's a breakdown of the main areas operators manage. A. Provisioning. The first role of an operator is provisioning. It ensures that the application is deployed according to the custom resource specification. This includes deploying pods, managing storage, and configuring network access for the application. For example, the operator might be responsible for provisioning the initial set of database nodes for a new Postgres cluster resource. This could include setting up persistent storage volumes, initializing the database, and configuring any necessary replication settings. B. Scaling. Operators can manage both vertical, resource-based, and horizontal, replica-based, scaling. Horizontal scaling means increasing or decreasing the number of instances or replicas running. Vertical scaling adjusts the resources, CPU, memory, assigned to individual pods. For example, the PostgreSQL operator could monitor CPU usage and dynamically adjust the number of database replicas based on load, ensuring that performance is maintained as demand grows. C. Upgrades and patching. Many applications need to be periodically updated with new features, bug fixes, or security patches. Operators can automate rolling upgrades, ensuring minimal downtime. The operator can manage the complexities of rolling out updates without interrupting service by gradually upgrading one pod at a time and verifying that the update succeeds before moving on to the next. For example, when a new version of PostgreSQL is available, the operator can apply a rolling upgrade, one node at a time, ensuring that no more than one node is upgraded simultaneously to minimize the risk of failures. D. Backup and restore. Backup and restore procedures are critical for stateful applications like databases. Operators can handle automatic backups according to a predefined schedule. If a failure occurs, the operator can also manage the restoration of data from a backup. For example, in the case of a Postgres cluster, the operator might take daily snapshots of the database and store them in a Google Cloud Storage bucket. In the event of data loss or corruption, the operator could automatically restore the database from the most recent backup. E. Failure recovery. Operators can automate failure recovery processes. When a component of the application fails, such as a pod crashing, a node going offline, or a disk failure, the operator can detect the failure and take corrective actions. This might include restarting the pod, moving it to a healthy node, or restoring data from a backup. For example, if one of the nodes in a PostgreSQL cluster fails, the operator can automatically spin up a new instance on a healthy node and reconfigure replication to ensure data consistency. Popular Kubernetes operators. Operators have become a standard tool for managing complex applications in Kubernetes, and many organizations have developed operators for their software. Here are some of the most popular and widely used operators in the Kubernetes ecosystem. A. Prometheus operator. The Prometheus operator simplifies the deployment and management of the Prometheus monitoring stack on Kubernetes. It handles everything from deploying Prometheus instances to configuring alerting rules and monitoring targets. B. PostgreSQL operator. The PostgreSQL operator manages PostgreSQL clusters on Kubernetes. It automates tasks like database provisioning, scaling, backups, upgrades, and high availability configurations. C. Kafka operator. The Strimsy Kafka operator manages Apache Kafka clusters on Kubernetes. It automates the deployment of Kafka brokers, Zookeeper nodes, and ensures high availability and failover for Kafka consumers and producers. D. MongoDB operator. The MongoDB operator simplifies running MongoDB clusters on Kubernetes, managing replica sets, backups, scaling, and upgrades automatically. E. EatKD operator. The EatKD operator automates the lifecycle of EatKD clusters, which are a critical component of Kubernetes itself. It manages deployment, upgrades, backups, and recovery for EatKD clusters, ensuring that EatKD remains highly available and consistent. Securing your GKE environment. Security is paramount in the cloud, and Kubernetes offers robust security mechanisms, GKE-specific security best practices, including identity and access management, IAM, role-based access control, RBAC, and Kubernetes secrets. Monitoring, logging, and troubleshooting in GKE. Once your applications are running on GKE, monitoring and logging become critical for ensuring their health and performance. Google Cloud Stackdriver is used for logging and monitoring, setting up alerts. Chapter 3. Storage and databases, secure, scalable, and always available. Every application needs a place to store data, and with Google Cloud, you have several options depending on your use case. Whether you're storing large media files, transactional data, or real-time analytics, GCP has the right storage and database solutions. Cloud storage. Google Cloud Storage is the ultimate object storage solution for structured and unstructured data. It's ideal for storing everything from backups to large datasets for machine learning. Data is stored in buckets, which can be configured to meet your needs, whether it's low-cost archival storage with Coldline or highly available multi-region storage for mission-critical data. An example of cloud storage in action could be a media company storing thousands of videos and images. With cloud storage's ability to handle exabytes of data and seamlessly integrate with other Google Cloud services, this company can ensure their content is accessible to users worldwide while managing costs efficiently. Cloud SQL? For relational database needs, Cloud SQL is a fully managed database service that supports MySQL, PostgreSQL, and SQL Server. Cloud SQL automates backups, replication, and scaling so you can focus on your application's logic instead of managing the database infrastructure. Imagine a financial services application that needs to store transaction data in a relational database. With Cloud SQL, the company can rely on automated failover, backups, and disaster recovery to ensure their data remains safe, while maintaining high performance under heavy loads. BigQuery? BigQuery is GCP's enterprise data warehouse that allows for fast, SQL-based queries over massive datasets. It's serverless, meaning you don't have to manage any infrastructure. You simply upload your data, and BigQuery does the rest. Whether you're analyzing customer trends, running business intelligence reports, or conducting scientific research, BigQuery offers the performance and scalability you need. Chapter 4: Networking, Connecting Your Cloud Resources. A robust cloud platform is nothing without efficient networking. GCP offers advanced networking solutions that help you connect your resources, whether they're in the cloud, on-premises, or even in other cloud environments. Virtual Private Cloud? VPC. With GCP's Virtual Private Cloud, VPC, you can create isolated network environments to securely connect your cloud resources. VPCs are global, meaning you can set up and manage resources in multiple regions under a single network. For example, if you're running an application with front-end services in the US and data processing in Europe, you can configure a single VPC to span both regions, ensuring low latency and secure communication between them. Chapter 5: AI and Machine Learning, the Future of Intelligent Applications. Artificial intelligence and machine learning are driving innovation in almost every industry today. With Google Cloud's AI and ML tools, you can bring the power of machine learning into your applications, no matter your level of expertise. Vertex AI. Vertex AI is Google's unified platform for machine learning, helping you build, train, and deploy ML models at scale. It integrates seamlessly with other GCP services, allowing data scientists to focus on experimentation and model development without worrying about infrastructure. Whether you're building predictive models for customer behavior or training neural networks for image recognition, Vertex AI gives you the tools to succeed, with built-in AutoML features for those new to machine learning. Chapter 6: Security and Compliance, Protecting Your Data. Security is at the forefront of GCP's design. Google Cloud provides tools and services to secure your infrastructure, applications, and data. Identity and Access Management (IAM) allows you to manage access control by defining who can do what on specific GCP resources. With IAM, you can assign permissions based on roles, ensuring that only authorized personnel can access sensitive data or critical systems. CloudArmor? CloudArmor protects your applications from DDoS attacks and provides a web application firewall (WAF) to guard against other web-based threats. If you're running an e-commerce website during a major sales event, CloudArmor can help ensure that your site remains available, even under attack. Chapter 7: DevOps and Continuous Integration and Delivery. In today's fast-paced development environment, automating your workflows is critical. GCP's suite of DevOps tools allows you to implement continuous integration and delivery (CI/CD) pipelines, ensuring faster development cycles and more reliable deployments. CloudBuild? CloudBuild allows you to build, test, and deploy applications at any scale. Whether you're deploying a simple web app or a complex microservices architecture, CloudBuild integrates with your Git repositories to automate every step of the build process. Chapter 8: The Future of Google Cloud. As businesses grow and evolve, so too does GCP. From hybrid cloud solutions with Anthos to advancements in AI, GCP continues to innovate and lead the cloud computing space. The future of cloud is exciting, and GCP is at the forefront, providing tools that empower developers and businesses alike to solve their toughest challenges. Thank you for joining me on this journey through Google Cloud Platform. As you explore GCP's vast array of services, remember that the cloud isn't just about technology, it's about unlocking possibilities and building the future.